In the previous class, we talked about monoclinic material. So, today we will talk about other types of anisotropic materials, and one of them is orthotropic material. Orthotropic materials have three mutually perpendicular planes of symmetry. So, if they have two mutually perpendicular planes of symmetry, that automatically ensures that the third plane is also a plane of symmetry. Now, let us suppose we have this axis system 1, 2, 3, and in monoclinic material we saw that if this axis 3 is inverted and becomes 3 prime, then the same constitutive relation holds. And similarly, if I invert this axis 2 to 2 prime, just 180 degree angle between 2 and 2 prime, and then also the same constitutive relation holds, and this automatically ensures that a inversion of 1 would also give us the same constitutive relation. Now, so today we will see how many elastic constants can further be reduced by inverting this 2 to 2 prime. Now, in the last class we talked about monoclinic material, and then we already saw the conclusion of inverting 3 to 3 prime, and with that, so with that symmetry with respect to 1-2 plane, that gave us C14 is equal to C15 is equal to C24 is equal to C25 is equal to C34 is equal to C35 is equal to C46 is equal to C56. And those terms are 0. Now, we will invert that with respect to the plane 1 3, that means we will invert 2 to 2 prime. Now, for that the rotation matrix that we get R is 1 0 0 0 minus 1 0 0 0 1. So, 2 is rotated. So, the angle between 2 and 2 prime is 180. So, that gives us minus 1 here, and rest others we already discussed why they give 1 and why the off diagonal terms are 0. Now, with that inversion, the relations between sigma prime and sigma that we get is this. We have sigma 1, sigma 2, sigma 3, then minus sigma 4, sigma 5 minus sigma 6, and accordingly we have the epsilons, epsilon 1, epsilon 2, epsilon 3, all with primes, epsilon 5 prime, epsilon 6 prime, and that is epsilon 1, epsilon 2, epsilon 3 minus epsilon 4, epsilon 5 minus epsilon 6. So, now if I write sigma 1 prime, which is sigma 1, we get C11 multiplied by epsilon 1 plus C12 multiplied by epsilon 2 plus C13 multiplied by epsilon 3 minus C16 multiplied by epsilon 6, and with respect to 1 2 3 system we have C11 multiplied by epsilon 1 plus C12 multiplied by epsilon 2 plus C13 multiplied by epsilon 3 plus C16 multiplied by epsilon 6, and let us call it equation number 1 and equation number 2. So, all the terms that were found to be 0 because of the symmetry with respect to 1 2 axis, they have been dropped here. So, only the rest of the terms are written. Now, again following the same approach, if I just do 1 minus 2, that gives me 2 C16 epsilon 6 is equal to 0, and that says that C16 is equal to 0. Similarly, if I do sigma 2 prime is equal to sigma 2, and then we have C12 multiplied by epsilon 1 plus C22 multiplied by epsilon 2 plus C23 multiplied by epsilon 3 minus C26 into epsilon 6. And in the 1 2 system we have sigma 2 is equal to C12 epsilon 1 plus C22 epsilon 2 and C23 epsilon 3, and then we have plus C26 epsilon 6, and let us call this equation number 3 and let us call this as equation number 4. Now, if we do 3 minus 4, that leads to twice of C26 epsilon 6 equal to 0, and that says that C26 is equal to 0. So, all the shear extension couplings that we had for monoclinic material, they have vanished now. Now, let us do it for sigma 3 prime. So, sigma 3 prime is equal to sigma 3, and that we can write as C13 multiplied by epsilon 1 plus C23 multiplied by epsilon 2 plus C33 multiplied by epsilon 3 minus C36 multiplied by epsilon 6 is equal to 0, and in the 1 2 system we have sigma 3 is equal to C13 into epsilon 1 plus C23 into epsilon 2 plus C33 multiplied by epsilon 3 plus C36 multiplied by epsilon 6 equal to 0, and let us call this as equation number 5 and let us call it equation number 6. And then if we do 5 minus 6, then we get twice of C36 epsilon 6 equal to 0, which tells me that C36 is equal to 0. So, all the shear extension coupling terms are gone. Now, we can do this for sigma 4 prime, which is equal to minus sigma 4, and so minus C44 into epsilon 4 plus C45 into epsilon 5, and then we have sigma 4 is equal to C44 multiplied by epsilon 4 plus C45 into epsilon 5, and let us call this as equation number 7 and equation number 8. Now, if I add 7 and 8, that implies that C45 is equal to 0. So, with that, if we write the constitutive relation, it just looks like this. So, now we can see that there is extension coupling is present, but there is no extension shear coupling and there is no shear coupling. So, in this kind of material, if we apply a pure normal stress, then there is no shear going to be induced. So, after application of load, this will extend in this direction and this can contract in the other direction and other two directions, but there would be no shear involved. Now, we will talk about another type of material, and that is called transversely isotropic material. So, in transversely isotropic material, there is one plane in which the material behaves like an isotropic material. That means, the properties in all the directions are same. So, let us say this is our transversely isotropic material, and in this material 2, 3 is the plane of isotropy. That means, the properties in the plane 2, 3 in any direction, all the directions are same. So, an example of this kind of materials is composite materials which has fibers arranged in regular way. So, let us suppose that this is our composite material, and at this face if I look at the fiber cross sections, their arrangement is regular. So, with a regular arrangement of fiber cross section, we can see same configuration in whatever direction we look. So, that makes it isotropic. However, if the fiber directions are irregular, then it is not isotropic. So, a composite with regular fiber arrangement has transverse isotropy in one plane. Now, to look into this, let us suppose that we define axis system 1, 2, 3 and then we say that and our 2, 3 is the plane of isotropy, 2, 3 is plane of isotropy, and let us assume that we have a rotated coordinate system 2 prime, 2 prime and 3 prime, which looks like this, and the angle between 2 prime and 2 is alpha. So, if I see this in the 2, 3 plane, the system looks like this. We have the original system 2, 3 and we have the rotated system 2 prime and 3 prime, and the angle between them is alpha. So, it is a pure rotation with respect to axis 1. Now, since it is isotropic plane, that means the properties in any direction is all the directions are same. So, that is why instead of taking discrete 90-degree rotation, we are taking any generalized rotation alpha, and now with the help of that we will prove the properties of these materials. So, for that, if I rotate this system with an angle alpha, the rotation matrix corresponding to this is 1 0 0 0 cosine alpha sin alpha and then 0 minus sin alpha cosine alpha. So, here we can see the angle the axis 2 prime has an orientation alpha with respect to 2 and an orientation 90 minus alpha with respect to 3. So, that is why we see cosine alpha and sin alpha here, and the axis 3 prime has orientation 90 plus alpha with respect to axis 2, and the same thing has an orientation alpha with respect to axis 3. So, that is why you see minus sin alpha and cosine alpha. Now, with this rotation matrix, if I find out sigma 1 prime, that simply remains sigma, but the other terms like sigma, if I find out epsilon 2 prime, that becomes epsilon 2 multiplied by cosine square alpha plus 2 epsilon 4 multiplied by sin alpha and cosine alpha plus epsilon 3 multiplied by sin square alpha, and similarly we have epsilon 3 prime, and that is epsilon 2 sin square alpha minus 2 epsilon 4 sin alpha cosine alpha plus epsilon 3 into cosine square alpha. Now, if I put that in the stress strain relationship, then we get sigma 1 prime is equal to sigma 1 is equal to C 11 multiplied by epsilon 1 plus C 12 multiplied by epsilon 2 cosine square alpha plus 2 into epsilon sin alpha cosine alpha plus epsilon 3 sin square alpha. Similarly, we have sigma 1 is equal to C 11 into epsilon 1 plus C 12 into epsilon 2 and plus we have C 13 into epsilon 3 and the corresponding term here is C 13 into epsilon 2 sin square alpha minus 2 into epsilon 4 sin alpha cosine alpha and we have plus epsilon 3 cosine square alpha. Now, let us call this as equation number 1 and let us call this as equation number 2. Then if I subtract 2 from 1, this gives me a term like this epsilon 2 multiplied by C 12 sin square alpha minus C 13 sin square alpha plus we have epsilon 3 multiplied by C 13 into sin square alpha minus C 12 into sin square alpha and then we have a term minus 2 epsilon 4 sin alpha cosine alpha C 12 minus C 13 and that is equal to 0. Now, one thing to note is that these transversely isotropic materials are orthotropic. So, apart from being orthotropic, they have a special property that they have one plane of isotropy. So, because they are orthotropic, so there is no the coupling terms here, coupling between normal and shear terms. Now, with this relation, we can easily say that this relationship always holds once we have C 12 is equal to C 13. So, when C 12 is equal to C 13, these individual terms become 0 and this relationship holds for any choice of alpha or epsilon 2 3 or epsilon 4. Similarly, we can write these relations for different stresses and then do these operations and finally, after doing that the relationship that we get is this. So, this becomes our new stiffness matrix given that this material is orthotropic as well as they have one plane of symmetry, that means transversely isotropic. Now, we can easily see that because our 2 3 plane is transversely plane of isotropy. So, that is why the properties along direction 2 and direction 3 are same. Similarly, C 12 is equal to C 13 and again these shear coefficients are also same. So, 1 2 and 1 3 shear coefficients are also same. Now, let us understand the behavior of this material with a simple example. Let us say that we have a cube and this cube has, so this is a cube and this cube has dimension A multiplied by A multiplied by A. So, all the sides are A And let us suppose, so these are our axis system 1, 2, 3, and suppose we are loading it along direction 3. So, if we do that, it is going to extend in direction 3. So, this new dimension is going to be A plus delta 3 3. So, delta 3 3 means change in dimension along third direction due to a load along third direction. So, first index refers to load along which direction, and the second index refers to along which direction I am looking at the change in dimension. Similarly, this can be written as delta 3 1. So, change in dimension along one direction due to a load along direction 3, and this we can write as delta 3 2. So, this is A plus delta 3 1. So, this is A plus delta 3 2. Now, let us say that this same cube is loaded in direction 2. Say this loaded is this is loaded in direction 2. If that is so, then dimension along 2 becomes A plus delta 2 2, and dimension along 1 becomes A plus delta 2 1, and dimension along 3 becomes A plus delta 2 3. Now, finally, I will load it along direction 1. And if we do that, here we have A plus delta 1 1, that means new dimension along one direction, A plus delta 1 3 new dimension along direction 2, and we have A plus delta 1 2 the new dimension along dimension 2. So, this was along dimension 3, this is along dimension 2. Now, since the plane 2 3 is plane of isotropy, that means the effect of loading along direction 2 on direction 2 should be same as effect of loading along direction 3 on direction 3. So, which means delta 2 2 should be is equal to delta 3 3. However, direction 1 does not lie in any in the plane of isotropy. So, the effect of loading along direction 1 on direction 1 is not going to be same. So, this is not equal to delta 1 1. Now, let us look at the other terms. So, if I load it along direction 2, whatever influence it has on direction 3, that we call as delta 2 3. Now, the same influence a loading along direction 3 will have on direction 2. So, that means delta 2 3 is equal to delta 3 2. Similarly, if I load it along direction 2, then the influence that we have on direction 1. So, delta 2 1 that should be same as if I load it along the direction 3 and its influence on direction 1. So, delta 2 1 is equal to delta 3 1, but these two things are not going to be same as the previous ones. Now, if I look at loading effect of loading in direction 1. So, effect of loading in direction 1 on direction 2. So, delta 1 2 is going to be same as effect of loading along direction 1 on direction 3, because 2 3 is the plane of isotropy. So, that is just briefly says how this material behaves along certain loading conditions. Now, finally, we have isotropic material where we have infinite number of material symmetry. So, there are infinite material symmetry, and it has properties same along all directions. So, with that, because the properties are same along one direction, so we have C11, C22, C33 are same, and these normal extension couplings are also same. There is no extension shear coupling, there is no shear coupling, and similarly these shear constants, they are also same. Now, if I look at that same loading effect for a isotropic material, what we see here is this. Again, if I load it along direction 3, it is going to contract along direction 1. So, we will have A plus delta 3 1, and here we have A plus delta 3 and here we have A plus delta 3 Similarly, if I load it along direction 2, then we have this as A plus delta 2 that is the direction where it is extending. Other directions we will see some contraction, we have A plus delta 2 and we have here A plus delta 2 3. And then if we load it along direction 1, we have A plus delta 1 and this is a contraction, we have A plus delta 1 and this is also a contraction, we have A plus delta 3. Now, here we have infinite number of symmetries. So, whether the effect of loading along direction 1 on direction 1 is same as effect of loading along direction 2 on direction 2, that is same as effect of loading along direction 3 on direction 3. So, delta 1 delta 2 and delta 3 are same. Previously in case of, so this is not a transversely isotropic material, this is an isotropic material. So, previously in case of transversely isotropic material, we saw that delta 2 and delta 3 are same, but that is not same as delta 1, but here everything is same. Similarly, we can write the other terms. So, delta 2 is equal to delta 3 is equal to delta 1 is equal to delta 2 is equal to delta 1 is equal to delta 3 So, all these terms are same now. So, that is how an isotropic material behaves. So, with this I would like to conclude this lecture here. Thank you.